example number 1. This is just meant, these are both sort of simple. I'm doing these just as a sanity check to make sure the definitions make sense, but also I want to give you a couple formal proofs which you can then use as templates for your homeworks and exams and so on. So when I say I want a formal proof using big O notation, these next 2 things will be exactly what I mean. Okay, so they'll also serve that purpose.
Does T of n also have to be greater than f of n as in your picture?
T of n.
There's no could be order of n to 6 order of n squared. It just has to be.
It's only like a less than or equal to. Okay, so remember, so something like n is in fact big O of n squared. Okay, so it doesn't mean that they're close to each other. It just, so basically if you're big O of something, you might be way less. Okay, but you're not more. Just like when you say x is less than or equal to y, for all you know, x is way less than y. Okay? Saying x less than or equal to y is not saying it's close to y. Similarly here, we're not saying t of n is close to f of n. We're just saying it's bounded above by a multiple of n.
Saying something is order of n squared doesn't mean it's also not order of n.
Correct. Okay, and I'll show you the other variants of big O notation to try to get at that finer granularity. Okay? So the first example is just meant to formalize this idea that we can drop constants in lower order terms, that's what big O notation allows us to do. So the claim is that if t of n is a polynomial with coefficients, it doesn't matter, n is dominated. Okay, so then t of n is big O of n to the k. Okay, when you pass the big O notation, you can throw out the lower order terms and ignore the leading constant. So I'll show you the short proof of the fact and how you would prove something is big O of another. So, remember, how do you prove this? We need a winning strategy of C and N naught, so that no matter what they pick, they cannot flip that inequality. Okay? So, I'm just going to sort of pull a rabbit out of my hat, and I'm just going to show you the right choice. Okay, so we're going to just choose N naught equal to 1, and we're going to choose the constant multiple to be the sum of the absolute values of the coefficients. Okay, so I'm not AIs might be negative. Okay, so some of those might be -7 or something. But I take the absolute value of each and I add them up. Now, in practice, like when you do your homework and when you would be able to have a wild guess at what the right C and N naught. Imagine starting the proof. Okay, so either you could take a first guess, start the proof, see where it fails, go back and see as your choice of C and N naught, or you could just somehow do the derivation for a generic C and N naught, and then what would I choose C and N naught to be to make this work? So I encourage you to kind of, after class, go back to these proofs and say, how could I have sort of, without knowing C and N naught, reverse it what they should be? Just to keep the lecture kind of slick, and I'm just going to, tell you what the right answers are up front. And then we'll check if they work. Okay. So we need to show. Okay? So what does it mean to show that T of n is big O of something else? We need to show that for all n at least n naught, and here n naught is 1, so for all n 1 or more, n is at most C times n to the k. Right, so that's the goal. So we have, so fix your favorite value of n, at least 1. Right, so we're going to start. We need less than or equal to, and we want to end up here. Okay? Starting with T of n. What do we know about T of n? We know T of n is this thing, this polynomial. Okay? So let me ask you a question. Remember, so there are coefficients to this polynomial. N is some fixed number. N might be 1, N might be a billion, whatever. So let me say are positive, some are negative. What if I replaced each AI, each coefficient, with its absolute value? Would that number go up, go down, you don't know, or what?
These go up.
It can only go up, right, because n is positive. Okay, so if we take something that was a -5 and we flip it some, we make it 5 instead, it only gets bigger. Okay? So that means n is bounded above by the absolute value of a to the k, n to the k, plus yada yada yada, absolute value of a1 n plus absolute value of a naught. Let me ask you another question. Now, suppose I took some of those lower powers of n, n to the k minus 1 and 2, bumped up the exponent. I replaced them by n to the k. Down, you don't know. Again, it can only go up. But n is 1, so a higher power of n is only bigger. Now the coefficients are positive, so it only gets bigger. Okay? So this is, at most, absolute value of a to the k n to the k plus absolute value of a1 n to the k plus a naught n to the k. Okay, so again, and notice by our choice of c times n to the k. So it's not exactly, rich with conceptual insight, but this is how you prove it. Okay.